All right, we're recording with Josh Durgan giving a technical deep dive for RBD on Ceph. So Josh, if you'd like to take it away.
Thanks, Patrick. So today I'll be talking about RBD, the RADOS Block Device, and going into a bit of detail about how it works and the mechanisms that it uses from RADOS to do the things that it does. So at a high level, stuff is broken down into several different components. All built upon the low-level RADOS, and RBD in particular uses a number of features of RADOS that make it much easier to build something like RBD than it would without if you were building it on top of like a plain file system or without a nice consistent distributed layer beneath you. But today we're not going to be talking too much about RADOS, so I'm going to be assuming that you're already a bit familiar with how RADOS works, and if you aren't, basically just assume that you have a strongly consistent object store that gives you all kinds of different transactions and partial reads and writes that you can do. And for more details, you can go and watch Sam's talk in this series, which is on YouTube already, I think. So the RADOS block device is typically used as either something for storing disks for virtual machines. And in this case, it goes through the user space library, which is linked into a hypervisor like QEMU. And then on the back end, this talks to the Ceph cluster. And to the virtual machine, it just looks like it has a regular disk. It can't tell whether it's using RBD or local storage or anything else. The other main way of consuming RBD is via a Linux kernel module. And with this, you can map a RBD device directly onto a Linux host, and it just appears like a regular Linux block device. And you can mount it and put a file system on it, mount it, and do what you want with it from there. And again, it's just accessing the RADOS cluster on the back end, not using local disk at all. So the high-level features of librd are that it's presenting a block device interface, but it's actually storing that data across the entire cluster, or at least one pool in the cluster. It provides snapshots, which are read-only, and then copy and write clones if you want to create a copy of something quickly without taking up extra space, and being able to use a copy of a block device quickly. And it's integrated in a lot of different projects, including QEMU, libvirt, Linux kernel, as you just mentioned, a couple different iSCSI stacks, the TGT user space one and the LAO kernel one, and several different cloud platform or cloud management platforms, or whatever they're called these days, like OpenStack, CloudStack, OpenNebula, Ganeti, Proxmox, and Gopher is coming soon. It also provides incremental backup relative to snapshots, which is pretty handy for being able to take backups of things offline or online, since RBD, it also supports doing the snapshots online, and then you can do the backups based on those snapshots later. So that's kind of at a high level what RBD does, but how does it actually work internally? Well, before we go into detail about how RBD works, I want to just mention briefly how RADOS works. It's all built on top of RADOS. So the RADOS interface basically provides an API around doing transactions on single objects at a time, and an object being composed of bytes. It's a blob of bytes, like a file, but also a set of attributes and key value data. And RADOS allows you to do partial overwrites or partial reads of existing data, and also compound operations which are atomic on a single object. So you can do things like set an attribute and write some bytes to an object, or check that an attribute has a certain value, and if it does, then do an update atomically for that. It also provides a concept of RADOS classes, which are essentially like stored procedures in a database. What that allows you to do is load code into the storage daemons themselves, the OSDs, and call those methods from a RADOS client, and passing them whatever custom data format you want. and that's used extensively in RBD to kind of abstract away some of the low-level storage details. So that's kind of the basic interface that Liberator provides, and that's basically all that RBD uses at the at the highest level. So RBD has a few different kinds of objects that in which it stores data. First, it has the metadata in each pool where you have RBD images. There's an RBD directory object, which takes care of an index of a name to ID and an ID to name mapping for all the images in that pool. And that's handy just so you can list all the images in a pool. There's also, then for supporting cloning, there is an RBD children object, which contains a list of clones in a pool indexed by the parent. And that's just there so that you're able to tell when you're trying to go and being unprotect a snapshot that is used for clones, whether there actually are still any clones relying on that snapshot. So the way RBD does that is it goes through and looks at every pool and looks at all the RBD children objects in each pool, and just looks and checks whether there are any references to that parent snapshot there at the time when you're trying to unprotect it. It does this. It's slightly more complicated than that because it has to change the state from there's a tri-state for protection status of a snapshot. So there's no race conditions. So first, when it's unprotecting a snapshot, it goes and first sets it to the status unprotecting, which prevents any new clones from appearing. And then it goes and checks for any references to the snapshot in these RBD children objects. And then finally sets it to unprotected if there were no references. Then there's a few per image objects. These are just for format 2 images really, but format 1 isn't really too relevant anymore, so I'll just describe format 2. So format 2 has an RBD ID object, which is named after the user-defined name of the image, and that's so that you can go and look up what the actual internal ID is, so that RBD can support renaming of images without having to do complicated things with references like clones. So the RBD ID object simply contains the ID of the image encoded in Ceph's usual string encoding. And the main thing for storing metadata for an image is called the header. And this is named after the ID so that it's in the same object no matter what the name of the image happens to be. And if it's renamed, it stays the same. And this contains all the metadata needed to actually operate on the image, like the prefix used when accessing the data objects of the image, the size of the image, all the snapshots that exist in the image, all the metadata about the snapshots, any locks that are held on the image, things like that. The actual data in an image is all stored across usually a large number of objects, all beginning with the same prefix, and that they start with RBD data and then the ID of the image. And this is called the block name prefix, which is stored in the header. And then every one of these objects is named after, it's just named in increasing order from the start of the image. So starting at 0 through however many objects there are in the image. So you can just quickly calculate which object you need to read from or write to based on which offset you're doing I/O on in the block device. And RBD is thin provisioned, so when you create one, you have all these metadata objects, but you have no data objects at all. And so when RBD goes to read something from an object and it doesn't exist, it just treats that as a bunch of zeros, similar to how a file system would treat a hole in a file. So there's no existing state that's exposed when you create a new image. It's all zeros. And the data in these data objects is just stored as plain bytes in the regular byte portion of the object. There's nothing fancy going on with the format there right now. And the snapshots, which we'll talk more about later, are all handled by RADOS itself. It's worth noting that the RADOS objects in general can be sparse, and for RBD they often are. So even though RBD has the default stripings of like 4 megabytes, usually it'll be doing updates of much smaller sizes, and the whole 4 megabytes might not even be allocated or present. In terms of striping, by default, RBD stripes everything across a block device in 4 megabyte chunks, and that's just a simple kind of the largest size that you can do. It's kind of optimized for spinning disks, where you have kind of one seek's worth of data that you can get reasonably. These are kind of distributed randomly across the OSDs by crush. So one block device is spread across all the OSDs in the cluster potentially, or at least in one pool. And if you have lots of, that means you have lots of parallel requests to a given image. You're spreading that work over many spindles, so you're not bottlenecked on any one OSD. It also means that there's no single set of servers responsible for an image. So if you have some kind of catastrophic failure and you happen to lose like 3 nodes permanent because of 3 disks died at the same time, you might lose data for some images, but only a subset of them. And for a much larger subset, you only lost, say, 1 copy of data or 2 copies, and you can recover from that. Using small objects like these 4 megabyte objects is also important in RADOS in general, because of a couple of reasons. One is space utilization. Because RADOS is doing random placement, it's very important that there's not a very high variance in the utilization among OSDs, because if you have more than like one OSD that's getting too close to full, because we're doing randomized placement, we can't really tell when it's going to be safe to stop I/O from happening. Because if an OSD ever becomes actually full, it's quite a problem, because since we do journaling, we actually need to have some space there to be able to delete something. So having wide variance is a problem, because we need to actually block writes when the cluster becomes full, or when any OSD becomes full, since you may start placing objects there. So small objects help with the variance in space utilization, and they also help with just providing a large enough size that is reasonable to read in one seek, but not too large. So those are kind of the object structures and how the objects in RADOS look from RBD's perspective. So now I'd like to talk a little bit about the actual I/O path you have when you're going from a virtual machine all the way down to the RADOS cluster. So when a VM is doing I/O to its block, it'll first start out, if it's doing buffered I/O, it'll go through its page cache. Eventually, its kernel will flush down to the hypervisor, which will call out to librd. And if RBD has its cache enabled, it might, if it's in write-back mode, it might just respond immediately that it's fine, the write is fine because it's in RBD's local cache, which is in memory. And this, in that case, the guest will consider it successful if it's not asking for it to be flushed at that time. If the guest is asking for it to be flushed, or if after a few seconds, or if the cache is full, librd will start doing write back to the actual RADOS cluster. So if you have a 4K write coming down, it'll go into the cache as just a 4K, and if there's if there are no other writes that come in next to it before it gets written back, it'll get written back to RADOS as another 4K write to a RADOS object. It's worth noting here that the internal librd cache even though it's working in terms of objects, it's really doing finer grained things than that. So it's all just determined by whatever request the VM happens to send, how much I/O is done. It's not fetching or writing an entire object at once. It's only writing whatever the VM has requested and reading whatever the VM has requested. It's also worth noting about this cache that it's been recently enabled in by default in Hammer, but with an extra option so that it's in write back mode, it's in write through mode until it detects a flush from the guest. This is for extra safety. So it's to make it basically behave like a well-behaved hard drive cache. Even though it's in memory, all your writes will be flushed out to disk as the VM expects when the virtual machine actually sends a barrier down to the hypervisor or a flush request. And so that's exactly the same guarantee that a local hard drive gives you. But if the VM is too old, or if its kernel has the barriers turned off, then it won't send these flushes, and it won't be safe in the case of failure, and it might corrupt its file system or possibly lose some data. But some people run it in this mode for more performance. So that you can turn that off and turn off the flushes and turn off the safety in RBD, but by default it's in write-through mode, meaning that it waits for the writes to go all the way through the cluster before returning back to the VM until it actually sees a flush request, and that's what tells that the VM actually is probably being safe about sending flushes, and it can switch to write back mode. So the cache here mainly serves to coalesce writes and provide much lower latency for like bursts of writes that the VM may do, even if they don't overwhelm the cache. It helps quite a bit. And the read path is basically the same as the write path, except that if the data isn't in the cache, it has to go to the RADOS cluster immediately. It can't wait for that. I can't return to the guest yet because it doesn't have the data. So that's basically how I/O works from a virtual machine's perspective. So one of the more interesting things that RBD supports is snapshots, and these are actually done by RADOS itself in kind of an interesting way. So they're done on they're copy and write on a per object basis in RADOS, and the way that they're maintained is by having what's called a snapshot context, which is a list of snapshot IDs and the latest snapshot ID that an object was part of. So basically, whenever you take a snapshot, you allocate a new snapshot ID from the monitors, add it to this list of snapshot IDs, and send this snapshot context with every write to the image. And that way, you can do snapshots on a per image basis without having to do them across an entire pool. And doing these snapshots on a per object basis like this, or per image basis, is called a self-managed snapshot in RADOS, because we're managing the snapshot context and storing it at the RBD level. One other thing about snapshots is that they're actually deleted asynchronously. So when you delete a snapshot, RADOS will go and in the background add that snapshot ID to the OSD map as a snapshot that's been deleted. And as that OSD map gets propagated, the OSDs will in the background handle the deletion of the actual snapshot data. So it's not an instantaneous process. RADOS also helps us out even further by keeping overwrite statistics so that whenever there is a copy on write happening, it records what data has changed since the previous snapshot. So it's very simple to get diffs out of it, and that's how RBD incremental backups can work so easily. Just relying on the existing RADOS storage of that metadata about which things changed in a given object. Kind of going through the process to help you understand how the snapshot context works. So normally, so say we have an RBD image that has no snapshots yet. You'll know it'll have a snapshot context with an empty list of snapshot IDs, but the highest snapshot ID will be the highest one that's currently relevant for the pool. So let's say in this case it would be 7. So when you do a write, RBD will send the snapshot context with that write, and the OSD will note that there are no snapshot IDs, so it doesn't have to do any copy on write or any other work. If we create a snapshot, it'll allocate a new snapshot ID, and if this is the next one allocated in the pool, it'll be snapshot 8. RBD will then update the header for that image with that adding that snapshot 8 to the list of snapshot IDs, and increment since that's now the highest snapshot ID, putting that as a snapshot sequence number, the highest snapshot ID there. And then when it does any further writes to the image, it'll use that new snapshot context. And when the OSD sees that there's a write to an object at snapshot 8, which hasn't been written to yet since snapshot 8, it will go ahead and do the copy and write, and do a full copy of the object if you're on XFS or ext4 or most other backends. Or if you're on ButterFS, it can actually do a special ioctl on the file system clone range and save space there. But for the common case, with XFS, it's doing a full copy when it does the copy on write. And at that point, it knows that OSD has internally updated its metadata to be able to tell that it's done this snapshot for this copy on write for this object in snapshot 8, so it doesn't need to do that for anymore. But if there are other writes to other objects, it can tell based on its metadata that whether it needs to do a copy on write there for them or not. So that's essentially how snapshots work. But you'll note that if you're familiar with RBD already, you'll notice that this kind of you're able to take snapshots like with the command line tool while a VM is running or while the image is in use elsewhere. So you may be wondering how that works when you need to be able to send the snapshot context with every write. Well, for that, we take advantage of another primitive in RADOS called WatchNotify. This is basically a way for clients of LibRADOS to send very infrequent and small kind of communications to each other via RADOS. So basically how this works is whenever you open an RBD image, LibRBD or the kernel client will be setting a watch on the RBD header for that image. And whenever there is a change to some kind of information in the header, like the image is resized or it's flattened or a snapshot is added or removed, whatever is doing that update will notify other clients that are watching the same header via this WatchNotify mechanism, and they'll know that they need to then go and reread the header to see what's been changed. So for an example, if you have a VM using an image, it'll have a watch on the image, header object in particular. If you're creating a snapshot, say with the RBD command line tool, the RBD command line tool will also create a watch when it's doing the snapshot. since opening it for write. The RBD command line tool will add the snapshot information to the header. Like we just described, it'll allocate the snapshot ID from the monitor, then update the snapshot context, and save any snapshot metadata associated with it, like the current size of the image, the current features of the image, any other mutable state that needs to be saved with the snapshot. And then it will perform a notify. And the way notify works in RADOS is that the notify waits for all watchers to respond or timeout. So once all the watchers have responded with an ACK, the notify will complete, and the RBD command first will report success. After librd has gotten this notification that the header has changed, it will go back and when on next operation, see that it needs to update its metadata, its cache copy of the header metadata basically, and it'll go and reread all the information from the header before doing anything else to make sure it gets the most up-to-date like snapshot context and size and whatever else it may need. Now this WatchNotify mechanism has recently become even more robust in the Hammer release as well. So now it's actually a separate operation at the RADOS level. There's a watch2 operation which has slightly better semantics, where it actually reports errors. Like if the watch times out for some reason, the client, like normally previously the lower level thing inside of LibRADOS would continuously refresh the watch, but librd wouldn't get a notification if the watch timed out. But now with watch2 primitive in RADOS, if the watch does time out, librd gets a callback and it can tell that, okay, that watch has timed out. I need to go and reread the header data because I may have missed some notifications, and it reestablishes the watch at the librd level instead of leaving it to the LibRADOS level. So that makes these kinds of things a bit more robust. So the other major feature of RBD is not just snapshots, which are read-only, but clones, which are writable. So clones are also copy on write, but at the object level again. But they're done at the RBD level instead of at the RADOS level, because RADOS only supports transaction or atomic operations on single objects, and librd clones are kind of conceptually doing these for an entire image. So clones have can be entirely different settings-wise from each other. They can have different striping policies, different features enabled. They can use different objects. One can use 1 megabyte objects. One can use 4 megabyte objects. They can be in different pools. So you can have like a parent that's in for example, an SSD pool. If you have a very read-heavy workload, and you can have many clones of that data. And perhaps a slower pool because you don't expect many writes. And so you're actually just mostly reading from the parent and getting access to that fast pool. So clones are all based around a snapshot. So you create a clone from a snapshot, in particular a protected snapshot. I kind of mentioned this earlier before explaining really what what clones were. But so the protection basically prevents a snapshot from being deleted, so that you can make sure that you don't delete a parent image that a bunch of clones are referencing, which would basically corrupt them. So one way to the only way to remove that dependency on the parent image is to copy all the data from the parent, and that's done through a process called flattening. which is just triggering copy on write for every object in the clone, and then removing that parent relationship, including removing that reference from the RBD children object that we mentioned, talking about the RBD metadata at the beginning. So when you're doing I/O on a clone, if you're doing a read and the object doesn't exist, it'll just go directly to a parent. And when you first create a clone, again, since RBD is interprovisioned and it's copy on write, there will be no data objects in the clone at all. It'll just be the RBD header and the RBD ID, and the RBD header will have a reference to the parent snapshot ID by ID, the image by ID, and the pool by ID, so that those things could be renamed potentially, but the references would still be intact. And so whenever RBD does a read to the clone, it will notice that it gets back a response saying that the object doesn't exist, and it just goes and reads from the parent instead. Since these are copy and write, if you're doing a write and the object doesn't exist yet, we first opportunistically send an operation with a guard that says fail if this object doesn't exist, otherwise, and then do a write if it does exist. So if the object already exists, we just need to send one operation. If it doesn't exist, then we get back a response saying we need to go, the object didn't exist, and then we need to go and copy up the data from the parent and actually do the copy and write at the RBD level. So then we'd go read the entire object from the parent, or the entire logical portion of the parent that the span of which will be contained in the child object that we're trying to write to. And then we'll send a new operation once we've read that data, which does two things atomically. One is the copy up, which is writing all that parent data to the clone object, only if the object still does not exist. That's to protect from races where you might be doing copy up on the same object more than once at the same time. So you want to make sure that you don't clobber other writes at the same time. So we only copy the parent data if the object still doesn't exist, and then we do the write that was originally requested on top of that. So that's basically how cloning and snapshotting and pretty much all the I/O paths work today in Firefly and Giant. But I want to talk a little bit more about how you actually use RBD, and then go into more detail about what's coming in Hammer and in the future. So when you're using an RBD image, basically you need to be you're using it like any RADOS client, so you need a few different pieces of information. You need your authentication details, and for virtualization, this is usually stored by putting the secret key into libvirt's secret store. Then you'd have your VM definition in XML, feed that to libvirt, which includes all the usual other client information that you need to connect to a RADOS cluster, which is the monitor addresses, the client name if you have authentication enabled, and then there's some RBD specific and virtualization specific things like the QEMU block device cache setting. So, and this is also something that determines whether QEMU will send flushes down, whether or not the guest will supports it. So if you don't set the cache setting to write back in QEMU, or via this libvirt interface or via QEMU directly, even if the guest is sending flushes, the flushes won't be propagated to librd because QEMU will just ignore them. So it's very important to, if you're using write back caching, to enable the write back setting in QEMU as well as in RBD. And there's also the bus on which the device is attached in QEMU. The most common ones and the most recommended ones are RADOS Block or RADOS SCSI, since they have better performance than like legacy ones like plain SCSI or plain IDE. The one thing that RBD Block doesn't support is discard, which is like a trim operation on an SSD. It's just zeroing out a range of data from a block device. And RBD supports this, but QEMU doesn't let the guest actually use it unless you add some special QEMU options, which are kind of hard to specify and tend to change between QEMU versions. So it's not the best supported feature at the virtualization management layer yet, but it's there and it's usable. And you can use it through like RADOS, SCSI, or IDE buses. So this is kind of the how that picture looks from in terms of the VM setup and where it's actually running RBD. So your cloud management stack, or you manually would add give libvirt some XML to define your VM. Libvirt would translate that and configure things into a QEMU command line, and then run QEMU. QEMU would then start up, load libRADOS and libRBD, open the connection to the cluster, and start using RBD to connect to the cluster, open the image header, read the metadata, and then start up the guest and expose that device to the guest. So libvirt in most use cases isn't actually using RBD at all. It's just passing around some configuration data essentially. The one exception to that is when if you're using libvirt storage pools, which are actually linked to libRBD directly because they're about managing RBD images in general, or disk images, and so they can do some simple operations right now on disk images. I think they still can't. I forget if they can do clones right now or not. So that's basically what what a virtualized setup looks like in general. And there could be any kind of management on top of this setup. It could be CloudStack, OpenStack, Proxmox, Kinetti, many things. And some of them might even just call QEMU directly and bypass libvirt. In terms of the kernel client, it's a bit simpler. So RBD map is the command that sets everything up. It is a pretty simple interface that uses to talk to the kernel RBD device and actually get it to be visible, just going through sysfs. Then UDEV takes care of actually making a nice human readable symlink, so you can tell which device your image actually is, instead of using like the kernel automated dev RBD 0, dev RBD 1. So the kernel RBD is most useful for things that where you want to use the device directly on a host without virtualization. Like you might want to run some kind of application directly on top of it, or you might want to re-export it via iSCSI using LAO, or via NFS or Samba. It's probably worth noting, since it's caused some confusion in the past, that most of the RBD options, like RBD caching or pretty much all the other RBD options, are only applied to user space. This is because some of them simply aren't implemented in the kernel, and others, like RBD caching, aren't really relevant to the kernel, since for the kernel RBD device can take advantage of file systems on top of it, using the page cache like they normally do. So it doesn't really need that extra level of caching there. And the kernel RBD client doesn't quite support all the most up-to-date features yet, since we added them in user space first, since it's much easier to write them there and then get them into the kernel. So it does support clones and formatting images in general, but it does not yet support striping v2, which is striping in a more complicated fashion than just one blob of data, then the next blob, then the next blob. That's not there yet, but that's kind of more of a specialized thing anyway. And it doesn't support the newest features that have been added in Hammer yet either, since those are even newer. So let's talk about the roadmap and what's in Hammer and what's coming up in the future. There's a bunch of things merged in Hammer. Most of these are user space only for now. Some of them are off by default, but can be enabled in special circumstances or maybe more useful in an point release of Hammer. So copy on read is a setting that applies to cloned images, where instead of doing the copy up operation on a write, you could do it on a read instead. So instead of just reading whatever small, doing whatever read that the block device requested, if you only requested 4K, it would still fetch the entire object from the parent and then do a copy up in the background while satisfying the read immediate from that data it just read. So that's a nice way to speed up, copy up, and do it opportunistically in a bit of a more efficient way. If you know that you want to have these clones made full copies eventually, it's a more efficient way to do that. It's also useful for cases where you might have kind of an odd setup where you might have a cluster spanning geographic sites or a high latency between different sites, and you want to clone between pools, and then in that case you do want to copy up for having lower read latency, but then the copy on read lets you do that more efficiently by making it opportunistic and in the background rather than paying the penalty on every write necessarily. I mentioned earlier as well that we enabled the RBD caching in that safe mode where it's write back, but once it sees a flush, but it's right through to start out with. That's been something that's kind of been on the horizon for a while, but it's finally happened now. We've been recommending it to be enabled in this mode for a long time. Adam Kroom from the UCSC added read ahead support for RBD. So when you have caching enabled and you have a bunch of sequential I/O coming in because a VM is booting, for example, we do read ahead into the RBD cache up to 50 megabytes by default, or until the I/O stops being sequential. So the reason we stopped doing it after this 50 megabytes or this boot phase is because after that point, generally there's a kernel running inside the VM, which is going to be doing its own read ahead at that point. But during the boot up phase, at least for Linux and I think for several other OSs as well, there's not a lot of smarts in the BIOS or other things that are reading things at the very beginning of the boot process. And so this actually speeds up booting quite a bit especially for legacy buses like IDE, where it's doing lots of very small requests, and a little bit more for newer buses like Rodeo. Adam also added a bunch of LTT and G trace points to librd and librados, as well as a tool to, after collecting these traces, which basically gives you a view of all the I/O that's been done, not the actual data, but just when different reads and writes happened and how large they were and to what offsets. And so we can collect those traces now. And he also wrote a tool called RBD Replay to take those traces and play them back against a different RBD image. So you can benchmark performance against an actual known workload that you're running in your actual cloud, instead of just guessing using existing benchmarking tools. So hopefully we can start gathering traces from these from actual use cases and get more performance data that might actually be more relevant than synthetic benchmarks. Allocation hints are something that was added, I think might have been in Giant I can't remember, but I think it was disabled in Giant because there turned out to be a kernel bug in the way that in the XFS, because we're using the fallocate octal basically. When we send these allocation hints with the write, we're telling RADOS that we know that these objects are going to be 4 megabytes eventually, so just allocate them right now on the first write, so that they won't be very fragmented later if we were doing lots of like small I/O to them. So this seems to dramatically decrease fragmentation, at least with XFS. And in Hammer, it's enabled by default since the kernel bug in XFS was fixed, and we added some version checks to make sure that we only enable it when the kernel actually isn't affected by the bug. There are also some other hints added to the RBD read and write calls. These were done by the folks from Intel to give hints about the kind of I/O you're doing. So if you're doing sequential I/O or random I/O, or you explicitly don't want the data you're reading, for example, to be cached, you can specify that. And this is used to, within the RBD cache when it's doing write back now, to not waste the OSD page cache, because to not do any double caching there. And also by things like doing sequential reads and writes like RBD import and export. Since in those cases again, it's not useful to store things in the page cache in the OSD when they're only being read once. In the future, we might be able to use those on the Ceph level cache tiers as well. The last two features here are kind of the larger ones, which are right now off by default, since they're kind of newer and we want to make sure that they're really fully solid before we enable them. So exclusive locking is kind of the added to RBD so that when you open it, and a client tries to do an operation that is some kind of write, whether it's like creating a snapshot or doing resizing the image or just doing a plain old write or a discard, it needs to hold a lock on the header object. And this is coordinated with WatchNotify, as well as the existing RADOS lock class, so that we can make sure that operations don't, writes don't happen from multiple places. And so with this exclusive locking setup, whoever has the lock will actually get notifications from people or from other clients who are trying to do these things like resizing or flattening or creating a snapshot. And so those will basically be forwarded to the whoever has the lock and has the image open for writes already, and they'll perform the snapshot instead of having a different client do it. This also makes use of another mechanism in RADOS for extra safety, which is blacklisting clients. So if a client tries to open an image for writing, and it detects that there was an existing lock holder, but they no longer have a watch on the image, and they don't seem to be reestablishing their watch, RBD will go ahead and blacklist that old client, which at the RADOS level, which means that the client's address and nonce, which is unique per session, per RADOS cluster connection, basically, will be added to the OSD map, and the OSDs will refuse any operations from that client. So this provides some extra safety if you have some virtual machines that might be stuck running somewhere, and you thought they were down, and so you've already restarted them somewhere else. This exclusive locking will help and blacklisting will help with that kind of case. But more generally, it's a good groundwork for features that will require one client to be updating something in the future. So the first one of those is the object map, which is also new in Hammer and often by default. And this is basically an index of which objects exist in an image. And this is mainly a performance enhancement. So it will let you, since normally with, like, for example, with clones, when you're going to do a read from a clone, you have to check whether the object exists or not, and then go back to the parent if it doesn't. With an index of which objects exist, you can immediately go to the right place. And if there are several levels of parents, there aren't several levels of requests. It's just one request. Doesn't mean the object map is enabled for all of those. It will also enable things like better utilization tracking in the future, where you can actually see based on the object map which objects exist very quickly, and therefore roughly how much space is used in a snapshot, or how much space was added between this clone and this parent, or that sort of thing. So this is also off by default for now, because we want to make sure it's totally solid, and at some point, right now it's also only possible to use it for new images, but we want to add the capability to add it to existing images, or remove it from an image. If you wanted to, if you, for example, wanted to map it onto, use an old kernel client that doesn't support object maps and still be able to map that, you could just remove that object map from it and remove that feature bit, and then be able to use it with the kernel client. So those making those dynamic isn't there yet, but that'll probably be done fairly soon, and then hopefully be backported into Hammer in a future point release of Hammer. So in terms of things beyond Hammer, the largest thing is definitely RBD mirroring, which is the idea of asynchronous replication between different clusters. And that would also be built on top of the exclusive locking. So basically there would be a log of all writes done to an RBD image, and written out as they're happening. And then there'd be some other process reading that log and asynchronously mirroring those writes to a different image in a different cluster, or maybe in the same cluster in a different pool. That's all for disaster recovery across different data centers or different geographical regions. Another major thing that's in progress right now is work on active-active iSCSI support for high availability. This will require a bunch of upstream changes in LIO to be able to pass down some different levels of iSCSI error handling, and hook into the kernel RBDs to store persistent reservation information, and use some radius locking and possibly some blacklisting too. There's a bunch of other things in general that might be done in the future, but these are just the kind of things that I know are in progress right now, or will be in progress soon. So I think that's about it. I'm happy to answer any questions people have.
Awesome. Thanks, Josh. If anyone has questions, feel free to throw them in the chat, or you should be able to unmute yourself and ask them. Like we have one from Eric. What does the RBD kernel client do if a small number of PGs are missing or not accessible? Does it hang the device or give an IO error when it hits one of these missing PGs?
Okay, so in general, Ceph takes the approach of blocking rather than giving IO errors, because file systems don't really handle IO errors very well. So in any kind of condition where, like, an object is temporarily inaccessible because recovery is happening or the cluster is full, since the block layer doesn't have any way to report, like, that it's outer space, it'll just block those IOs and wait for that condition to be resolved. And hopefully that'll happen within a period of time that's acceptable for the application sitting on top of it, waiting for those to happen. When we use RBD volume from a VM, is the kernel driver not used? Yeah, that's right. So usually when you're using a RBD from a VM, you're using it with a QEMU, and you're just using librd directly and not going through the kernel driver at all. So QEMU is linked against like librados and librd, and it's just calling RBD write and read directly from that user space process.
All right. Are there any other questions? Looks like a no. All right. Well, thank you very much, Josh. This is great, and this should show up on YouTube here within the next day or two. So,
all right.
Stay tuned, and we'll see you guys next month for the next Ceph Tech Talk.
Great. Thanks, Patrick.
I believe is Yehuda talking about the RADOS gateway. So we'll see everybody then.